Hi, everyone. This is Evan McLaughlin. I'm a content marketing specialist with Minitab. I want to thank everybody for joining Seeing the Unknown, Identifying Risk and Quantifying Probability with Monte Carlo simulation today. We're hoping we can help you use what you learn to foresee all the likely scenarios that come out of changing your input. Before we get into the presentation, I do want to give out a few notes. This webinar is being recorded, so if you need to drop off in the middle for whatever reason, or if you'd like to share it with your team or review the content later on, please look out in your email inbox in the next few days. We'll be sending out the presentation slides as well as the recording. Also, please feel free to enter questions anytime in the questions pane in GoToWebinar. Myself and my colleague Savannah will be answering them online where we can. We'll also have a few minutes at the end of the webinar to cover more questions that we think would be great for everybody to hear the answer to. And also, just to make this a bit interactive, we're going to have a couple polls throughout the webinar for you. So when our presenter Jen puts up a poll, please go ahead and take the next few seconds to answer that. It'll help us kind of tailor the conversation for you. For those of you who aren't familiar with us, I wanted to say a few words about Minitab as well. For over 40 years, Minitab has been a leading provider of quality improvement and statistical analysis software. Over 90% of Fortune 100 companies use Minitab software to improve their products and their processes. Distinguished companies and organizations that rely on Minitab software and services include Ford, the Army's Lean Six Sigma program, Bridgestone, Xerox, and a few others that we have across the screen here. You can also see case studies on minitab.com detailing our work with these people and several other companies that we work with. And to introduce our presenter for today, Jen Atlas. Jen is an expert statistician with over 20 years experience in the quality improvement and consumer goods industries. So I'll hand it over to you, Jen.
Great. Thanks, Evan. Thank you, everyone, for taking the time for the session. So we're going to talk about Monte Carlo methods today, and I just wanted to start by saying, you know, Monte Carlo is really an umbrella term that covers a lot of algorithms that really use random number generators to approximate specific probability distributions. The reason I say that is we're going to cover Monte Carlo simulation, but think about it as Monte Carlo kind of 101. We're going to start with, you know, really talking about Monte Carlo simulation and how it works, but just be aware that there's a whole bunch of things that are considered Monte Carlo and a lot of methods that are a little too advanced for the nature of this webinar. But I think getting a good appreciation for how Monte Carlo simulation works and some of the tools it can solve really is something I think that you'll benefit from. So the technique was actually developed by scientists working on the atom bomb in the late 40s. It was named for Monte Carlo, the resort town in Monaco, where it was famous for its casinos. But really Monte Carlo, and really what I'd like you to get out of the webinar is just consider this another tool that you'd consider in your toolkit in terms of being able to solve some problems. And we'll talk about some of the problems you can solve, and you can think about how you might use this in your own day-to-day work. So really, Monte Carlo is an estimation procedure. It's really to estimate uncertainty, like I said, any kind of simulation to really get an idea about what might happen in a process or a product or anything without actually going out and collecting that physical data or in support of that. It really, like I said, we'll go through an example here in a second, but it's really about providing expected values for a response, giving some set of equations. So given that I know something that explains the behavior of some process or system, what kind of expected values might I see over the long term for some process? And it's really about, like I said, quantifying uncertainty. So when I say quantifying uncertainty, you know, how we're going to be doing this and looking at input variables, one of the things we'll need to talk about is basically what we're going to do is we'll have some equations and we'll take those equations, then we're going to, like I said, consider the uncertainty in those inputs. And those inputs could have different probability distributions. And it's not so much the statistical probability distributions that's important. What's really important from a practical standpoint is understanding if I've got some variable that I'm studying and I want to include it in Monte Carlo, really understanding what's the best way to estimate that probability distribution. How do I know what that distribution is? And that's an important problem that you really want to take some time to think about. So if I'm looking at some process and one of the factors in my process is temperature at some point in the process, really understanding, well, if temperature, instead of setting at some set point and it has some variability, what does that variability look like? What is the shape of those temperature ranges? If I could collect that data and look at that, what would that be? Is it, more of a normal distribution where it's peaked at some point and has, kind of symmetrical, bounds on either side? Is it more of a uniform distribution where the probability is equally spread over some range? So there are a lot of different distributions that you can consider and that we'll talk about, but really the important part from a practical standpoint is really getting, understanding how do I estimate that? Because if you think about if I have some data, and like I said, as we go through this, when you collect data and you think about things like process capability or just distributions, I want to estimate a distribution that, is stable over time in terms of what does that thing look like if I collect data throughout an hour, 2 hours, 5 hours, 5 weeks. Because if I'm going to be using this simulation to make some guesses as to what's going to happen in my process, I want to make sure I get some of these basics right. But I'm going to go through an example to talk about that. So I thought it might be good to start off with a pretty simple example that even if you're not involved in project management and risk, that everyone is involved with projects and has been affected in some way by projects that run over, finish early. But anyway, so if we think about any kind of process, I'm going to use DMAIC process here just for example. But the classic DMAIC, project would go through the different stages of defining and scoping the project, your MSA, your project baselines. And here I'm keeping it pretty simple, just for, like I said, the example purposes. But I could go into more detail with these for analyze. I could break it down into the, developing theories and thinking about potential root cause and analyze data and then verify root cause and understand cause and effect. And we really could make this a lot more complex in terms of what the actual steps of a project go through. But really, if you think about this is really, the steps of this process. And if I'm looking to measure a response, which is the total time it takes to complete a project, the transfer function or the equation that describes that is really just the sum of those factors. So just however long it takes to do each one of these phases, the sum of that would predict what the project duration might be. So like I said, simple example. Let's say hypothetically that for each of these stages, on average, I know that, the define phase might take about 5 days. The measure phase takes about 10. Now the question is, okay, if you're in charge of scheduling, if you're, setting this up, how do I predict, on average, how long is the typical project going to take? And if I'm going to sum these numbers up, typical project's going to be 33 days, just summing that up. So my predicted project duration, just looking at the model, from a completely deterministic standpoint would be, this is where I would think it would come in. The thing that's not being considered here, and this is where Monte Carlo is going to be able to help us, is that now I'm going to say that, okay, well, maybe on average define takes 5 days, but I know it's not exactly 5 days. And again, I'm rounding a lot, just assuming business days. But now I'm going to think about, well, what is the true variation? What's the shortest defined could be? What's the longest it could be? And what's the average? What does that come in? And I'm going to do that for each one of those inputs in my model. So like I said, here, I'm looking at predicting project time, but we'll look at another example, more of an engineering type application. But the idea is still the same. I have some input, and I want to be able to estimate what the variation of that input might look like. So if I focus just on that define phase for a second. So that define phase, I'm going to define it using the triangular distribution in this case. So remember I talked about the input variables and how important it is to get the distribution of those input variables right. A lot of times in project planning, the triangular distribution is common because you define it by a lower and upper bound in some mode, where it's most likely to happen. And I just generated a quick histogram here in Minitab just to show you what that distribution might be, where a lot of times in, let's say, non-engineering type applications where it's less where I'm just, like I said, I have some rough ideas about how things are in terms of where things might be. So in this case, I'm setting this up and saying, okay, so my defined phase usually takes about 5 days. There is a probability that I can get it done in as early as 2 days, and there is some likelihood that it takes as long as 12, although that's certainly not as common or frequent. And I'm going to do this for each one of these steps in this process. So here I'm looking at the project duration, again, still that full model, and I'm now looking at each one of these steps in my process, or each one of these inputs in the process. And for each one of the inputs in the process, I'm going to assign some uncertainty. And this is the uncertainty. This is where these distributions come in. So I'm going to assume for this type of process, project management thing, that each of these stages really follows a triangular distribution with some different settings on the parameters. So you can see, for example, the improve phase. I'm going to say that the mode is it usually takes 5 days. Maybe it could be done as little as 3, but going out 45 is not unheard of. So you can see that triangular distribution, while still triangular, looks a lot different from the others. Okay, so now I have like I said, I have my equation, I have my inputs, and I have some uncertainty for these inputs. And now, really what Monte Carlo simulation does is that I'm going to go ahead and randomly select, an item from each one of these steps of the process and just plug it into the equation and see what I get. And I'm going to do that 1 to 50,000, maybe a million times. I'm going to do that over and over. This idea of repeated sampling to really get a good idea of what's the worst case, best case on average. What kind of results might I expect for that process? And that really is what Monte Carlo is. One of the questions I got was, why am I using the mode versus the mean? For the triangular distribution, we define it using the lower, the upper, and the mode. If I'm using other probability distributions like the normal distribution, then of course we'd use the mean to define that. So it just really depends on what distribution you're looking at and what are some of those assumptions. Okay. So let's say that I want to estimate what percentage of projects are going to go over 60 days. So let's say, like I said, if I just straight sum, and let's say from a project planning standpoint, resourcing, I'm going to assume every project's going to last about 60 days. Anything longer, I want to know, to get an idea about, it's going to take up more resources, more time. Obviously, schedules are going to slip. And now what I'm going to do is just, like I said, run that simulation. So this is a snapshot of companion products, and you can do Monte Carlo in Minitab and work it through. You can do in other packages as well, obviously. But really what we're doing here is we're going to estimate what percentages are expected to go over 60 days. This is a snapshot of what companion looks like, and I'm not going to spend a lot of time in the software specific, but just to give you an idea. So here is the, my inputs that I'm defining my inputs, and I'm saying what kind of distribution they have. And like I said, I showed the list earlier, but there are a lot of different input distributions that you have. There's also the option in companion to use a CSV file to use the data to decide to to see if there's a distribution that fits your data that you have. But really the important part for you, so much not about using the software, it's more from the practical, where do you get that data to decide what that distribution is of that input distribution? Because that's the important part. If you have 5 numbers, that's not a lot of data to estimate that distribution. So I think you want to think carefully about where do you get that data? How do you collect it? How are you estimating what that distribution is? And really what those parameter settings are. So there, and here I have my equation. So you set your equation, and like I said, this first example, very simple equation where I'm just summing up each of these different steps. I have an upper spec of 60, and here I just have a visual of that model. Just I have these 5 different inputs coming into one output. So then I would click simulate. And here what the simulation results are, it looks like a histogram, but really what these are the results of each one of those iterations. So in this case, I've run 50,000 simulations where 50,000 times I've went and sampled from those inputs and plugged it into that equation. And this is what that distribution looks like over that, over time. So you can see that on average, I'd expect the average project to last 52 days. But given the distribution, given the variation in those inputs, that you'd expect about 25% of those projects to go longer than 60 days. Within Companion, we also show you the process capability, just to show you how that comes in. But again, if you're not doing process capability, it's really not that important. There are other summary statistics as well that you get by default things like percentiles and stuff. I'm not showing them here, but they're easy to open up. So like I said, so given the process, you'd expect about 25% to go outside of spec. So really the benefit, like I said, in this example was, here we're using Monte Carlo simulation to help you with modeling, analyzing, really improving how confident you'd be in terms of projecting, project times. So they can really use them to help to manage the risk in a project. The important part of this example, or any actually simulation that you'd run, is really the importance of getting the equation right. We also call them transfer functions within Companion. There was a question that how did I get an N of 50,000? That's our default within Companion. So within Companion, you could run anywhere between 1 and 1 million simulations. Our default 50,000, it gives you really good estimation, usually fills in the distribution pretty well. But there's really no, standard. A lot of other, earlier, 10 years ago, you'd see stat packages running, 2,500 values, 5,000 values. I think that was because of computer limitations. Now there's really not a reason to run such small sample sizes for simulation anymore. So 50,000, I think, is pretty standard, gives you some pretty good estimation. The maximum sampling size is 1 million, is what you can run within Companion. And you can run those up. Let me show you some more examples. So we have some different applications of Companion. And as I go through this, I just remembered that I was supposed to do a poll, and I totally forgot. And Evan is so nice to not interrupt me. So maybe we should do the first poll right now, Evan. Thanks.
Yeah, that sounds good. So yeah, we're going to put up, our first poll is, have you used Monte Carlo simulation before? So if you guys could go ahead and take a moment to click yes, no, or I'm not sure. We'll give you the next 5 or 10 seconds. See, and it looks like we have about 37% yes, 60% no, and 3% I'm not sure.
Excellent. Great. Okay. So like I said, so I think that was a good example to kind of get introduced into the idea, because now we'll talk about some of the more complex applications of it, but really the idea, once you understand the idea of Monte Carlo simulation, it's really the same. The models get more complicated. We could become more complex in terms of how many inputs and how many outputs and how we, put those things together. But really, it's the idea is that with Monte Carlo simulation is you're randomly sampling from inputs and taking into account the variability in those inputs to really get better estimates for your equations. So, we talk a lot within statistics and predictive analytics, fitting regression models and using some model to predict or explain some process. This is just kind of taking the equations a step further and saying, okay, well, now let me assume that there's some variability in those inputs. They're not, even though the assumption for regression is they're fixed, I know in real life that they're never really fixed sometimes, so I want to take that into account. And if I could take that into account and assume that, really build in the variability that might live within those inputs, it's really going to give me the ability to make better estimation, better prediction as to what the value might be. So there was a lot of different applications of Monte Carlo, and I wrote a couple up here, but again, really useful in predictive engineering work where you're looking to combine as you're doing product development. It's very expensive sometimes to make a lot of prototypes. You can do a little bit of work, do some simulation, get some new points, try that, and iterate, and really going back and forth between, making real things and iterating back over. So like I said, the concept of Monte Carlo is generally straightforward, although, like I said, depending on the complexity of the problem, and I'm talking about the transfer function of the model here, the approach can be difficult and time-consuming if you're doing it by hand. Computer packages make it pretty easy now. So as I was getting ready for this webinar, I was talking to a friend of mine who's an electrical engineer for a defense contractor, and he said that I should stress the fact that this is another tool for your toolkit. It's another tool in your toolkit. It's not the only thing you're going to want to use, but it really enhances product development and really helps, you make better decisions in kind of a way that's not so, you're making good decisions while you're doing product development, but you're not spending a lot of time just creating, product and things like that. But it's also good, like I said, there's so many applications for it to get better, assessment. Like I said, in finance, estimating stock values, all kinds of things. A lot of healthcare applications. Like I said, most of my experience is in engineering manufacturing side, looking at predicting viscosity of a product, any kind of engineering measures you look, and also trying to optimize, think about, if I make something like a dish detergent, I might measure viscosity, but now I'm also going to measure color, and I might measure the smell, and I might measure other, attributes of that product. Now when I'm looking at, optimizing that product and figuring out the best settings, it's really, I'm going to optimize, but incorporating simulation in that adds a little bit more, where it's going to take into account the uncertainty in those inputs for those different equations and really give me a good idea about what's happening. All right, so we're going to do the second question, and I've remembered this time to do my full question, so go ahead, Evan.
Sure. So we're going to ask you guys, which of the following types of analysis have you used before? DOE, design of experiments, regression, both DOE and regression, or none of the above. So take a moment here to answer one of those four options right here. All right, we've closed the poll, and we have 10% have used DOE before, 14% regression, 70%, that's a good amount, both DOE and regression, and 6% none of the above.
Perfect. All right, great. So another definition or way to think about simulation, and probably the one that you don't want to use when you're convincing people at your company to convince you that you want to do simulation, but it's really a fictitious representation of reality. And the only reason I bring it up is, like I said, it's not something you're not going to sell anybody by using this definition of it. But the thing is important is keep it in mind that it is simulation. It's virtual. You're guessing. It's really not, you're not making a final product decision based on the results of simulation or optimization. It's really there to help you to go back and confirm. And those of you who've done DOE or regression, you understand the value of confirmation runs, where we talk about it's really important that no matter what settings you recommend, that you go back and try that setting at a later point in time just to make sure that this is good value. So now what I want to do is go through another example. So the first example was really just applying Monte Carlo in, like I said, pretty basic application of project planning. Now we're going to do is take it into an example where we're going to incorporate DOE and regression, more of an engineering type application, where I'm going to apply it here. And we'll also talk about things like parameter optimization, sensitivity analysis. Okay, so we're going to go through an example with roofing shingles. And roofing shingles, if you're not familiar with them, there's asphalt roofing shingles, pretty popular within the United States, where they get put on a roof. They're made of asphalt, like I said, and the goal is obviously for them to stay on a roof for at least 30 years and continue to look nice and not cause any leakage on the roof. So they do some measurements on that, and they do some process. And if you think about, if I was going to be working on a process where my goal is to improve the response, and this response is granule loss. It's basically a scrub test where you take a shingle, you scrub it, you measure how many granules come off it, and that's a pretty good predictor that correlates pretty well with the lifetime behavior of that shingle. So I really want to look at what are the factors that affect granule loss. Now in this case, I've got an example where, when I was doing the project planning, I knew what the equation was. I knew it was the sum of these different components, and that's the total time it's going to take to complete the project. Here I'm talking about an engineering application where maybe I don't know what the factors are at first. So we're going to make some assumptions where if we were doing this in a 1 or 2 day class or maybe a week class, we'd go through the steps of, brainstorming the factors and using, fishbone charts and all those kind of tools and process map to really think about what this process looks like and really think about what those factors are. But I'm going to fast forward that and assume that I've done all that work, and I'm telling you that these are the 6 factors that I think are significant on the process. So they're different things, and if you've probably never seen this process unless you work in the roofing industry, but basically almost looks like a sewing machine where you thread some of the paper is coming in and they get cut, and there's things where it's like an assembly line where you're putting this paper through, you're coating it, you're dropping the shingles on, you're pressing the rocks on there, and then like I said, there's all these other things, and it moves at a certain speed. So here are these factors that we're studying, and like I said, if you're familiar with DOE, we're going to use a fractional factorial design for this. So the factorial design would, large number of runs, but a fractional factorial, I think it was resolution 4 design, which means that my main effects are only confounded with my 3-way interactions and my 2-ways are confounded with each other. But basically to be able to get some good information about what's going on. Okay. So really, like I said, to do Monte Carlo simulation, I'm going to assume that we've created the design of experiment, run the design of experiment, and here I'm really jumping to developing that transfer function. So here, getting that transfer function right, as with anything, any model that you want to use to describe any process, it's really important to get that right. So here I'm going through and I'm analyzing that factorial design, and I'm fitting this model where, figuring out what's important in terms of that process that really affects the granule loss of that shingle and what's not. Okay. So here's that model fit. So I'm just taking pieces out of the Minitab 18 output, where you can see the model summary, if you're familiar with regression. So pretty good model, very good model actually, describing the model, pretty good predictive power, and that the regression equation is here. So this is a case where, in the first example where the model was easy, define plus measure plus analyze, here the model is something that the engineer might not know off the top of her head in terms of setting this up. So, so here's my regression equation in uncoded units, and you can see that I've got some first order terms, the main effects, but then I've got some higher order terms, some interactions in here as well. And when we think about how we explore data and we take a look at it, lots of tools in Minitab statistical software that would help you understand those interactions, visualize them, really figure out what's happening on that process. What we're going to do now is we're going to take this model a step further, though, and think about, let's incorporate simulation and the uncertainty and really understand better, where do I think granule loss is going to be? So one of the things I need to do is think about, well, what are the distributions of those inputs? So once I've identified, using root cause analysis, whatever the different methods are, to identify these are the factors that are important, now one of the hard things is I really need to figure out, well, what are the distributions of those inputs? So again, this is where you're going to spend a lot of time thinking about, where am I going to find some data or get some data to decide this? This could be based on process knowledge. This could be based on raw data that you're pulling out of a database somewhere, or some experience. The one place I wouldn't get the distributions from would be the DOE, because your design of experiments only has 16 runs in it, or whatever, very limited amount of data. And obviously in DOEs we specifically set factors at specific levels, so that would be a terrible place to get the data. But like I said, you want to get some general, process behavior data to see what's been happening with that factor. So here I'm just showing you the graphical displays of some of these different factors, and you can see that some of them appear more normal, some of them might be more of a uniform. And again, I realize it's not always that easy where you create a graph and it's really obvious. So that's where you can do identification, distribution identification in Minitab, or like I said, in Companion, we have the ability to use data to decide, and just you can let it pick the data for you. So if we think about how we finish analyzing this data in Minitab, we fit a DOE, we check the data, we look at our regression model, we check residuals, and then we usually go to the response optimizer. And that's a great approach. So I go to the response optimizer, and if you're not familiar with the response optimizer, we can certainly give you some more information. You could let us know. But it's an interactive profiler that really allows you to explore the model that you fit and give you some prediction. So in this case, my goal is to minimize the granule loss, and I set some bounds on there in terms of what my target is and what my upper bound of acceptability would be. And running through that, you can see that for each of these factors, in red is where you're seeing the settings. The question was, I've got a question that is the model a result of regression or DOE? In this case, it's the DOE platform generated that model, but it really is like a regression model. I mean, depending on the nature of your terms, but in this case, it was design of experiments that generated that model. Okay. So here the response optimizer, and you think about, so here are the set points for the inputs. These are the optimal set points, and it's saying, okay, if you set your factors at these levels, you plug those into that equation that I showed earlier, that your predicted value is 190.2. So it's saying that if you could get your factor set at these settings, then you would predict that you could get granular loss set here. But we all know that the reality is that, well, this is nice, and this gives us an answer. It doesn't take into account the uncertainty. So straight optimizers or profilers really don't incorporate the fact that there's uncertainty in each one of these. What if I can't hold moisture at 0.5? What if viscosity doesn't stay at exactly 2000? So what I'm going to do now is, like I said, kick this up and take it into some Monte Carlo to really get into fitting that model and getting a better estimate about where's my average value going to be, really how capable is this going to be. So from an engineering standpoint, I really need to know how capable this process is. So what I've done is I brought that equation over into Companion. So Companion is in our Monte Carlo simulation is in the Companion tool. So the way I brought that in is you can just copy and paste the equation from Minitab and paste that into Companion. Here I've entered my input variables, and this is where I've done some work to say, okay, for each one of these factors, there's some distribution that was appropriate. So you can see here I've got some different distributions I've incorporating. In this case, the viscosity follows what's called a truncated normal distribution. The truncated normal distribution is a normal distribution that gets chopped, for whatever reason. Sometimes you cherry pick certain parts of the distribution for different customers, or sometimes just the nature of the process in terms of how it works. Putting that in for the filler, I've got a normal or uniform distribution where, it's just equally likely across the range, and some other normals. And like I said, within Companion, there's a lot of different options for different distributions that you can use. In general, I see most people using normal, uniform, and triangular, although, again, it's hard to say in general depending what your job is and what industry you're in. So here's the equation that I fit for granular loss. And like I said, I fit this with DOE. If I fit this with regression, would have had the same, and get the same results. Regression also takes into account interactions and things, also. So it's, like you said, you're going to get very same results, actually. So here I've got my input distributions. I've got my transfer function. So in this case, I've just got a single transfer function. After this example, I'll talk about how this could be extended. And then I've got my, what we call the visual validation. It's just a place where you can see what that model looks like, just to make sure it's specified correctly. So in this case, this is a pretty simple model with, 6 inputs and 1 output. But you can imagine that, what if I have, 6 input, what if I have 20 inputs and 10 outputs? And how do I build those models, and how do I put those in? We can put those all into the simulation tool within Companion. So there is no limitation to the number of inputs or outputs that you have within that tool. So it just depends on how much you have to build that up. Okay, so I've got my simulation. I've got this set up. I'm going to run 50,000 iterations of this. And here you can see that these initial results for granular losses. So here's my distribution. Values could be as low as down near zeros or about 50. But then granular loss values higher than, up near 300 are possible based on the data that I have. So remember, the importance of this, the specific example, is that it's really assuming that I've got the distributions right for those inputs. It's assuming I've got the equation right. So that's where you're going to spend a lot of time. Doing Monte Carlo simulation, once you've got the hard work done, it's pretty easy. But getting the equation correct and getting the input distributions correct is important, because otherwise, your simulation really isn't going to be that useful if the underlying assumptions are incorrect. One of the things you'll find within Companion is that we try to build in some guidance within this tool to kind of tell you what that next step is. So for the other example we were doing, project planning, there's not really a optimization. There's some sensitivity plots we can take a look at, and we'll look at here. But really, if you think about engineering, I run through a process and I've said, okay, here's my process. This is where I think I'm at. Right now, I'm predicting about 2% of these shingles are going to be out of spec based on this simulation. That corresponds to a capability statistic less than 1, which isn't great. So then the idea would be, okay, so what do you do? there's different options in terms of what you could do. The first thing we recommend, and usually the easier thing from a practical standpoint, is to assess, to look at parameter optimization. Can I tweak those parameters? So think about similar to the response optimizer, but the parameter optimization in Companion is really going to take into account not only that model, but it's going to take into account the uncertainty in those inputs and really try to find a better setting depending on what the objective is that you set for. So in this case, I'm going to go through and I'm going to try to find, are there settings for those input variables that I can control? So now that I've taken the time to, create this DOE and fit this model, are there settings for those inputs that I can change that would give me better results for granule loss? And this is what the parameter optimization is going to help us with. It's a genetic algorithm that runs through. Like I said, it's a little different than our response optimizer in Minitab in that it takes into account the uncertainty in those inputs as well as the predictive model that you fit. So the parameter optimization, so the parameter optimization, which I thought was here. That was the other result that I showed. So the parameter ranges is one thing you need to do is first define, well, what's your objective? So my goal is to minimize this variable, this output granule loss. And depending on what your objective is, it might be to maximize something, might be to hit a target. That's going to really obviously set the way the algorithm is going to run and try to find settings that satisfy those objectives that you've got. But then what I need to do is I need to provide search ranges for those parameter values. So really, as I'm going to be able to change the press, how do you pick, how do you set those values? So remember, as I'm picking this and I'm thinking about how do I pick the right distributions? Picking the right distributions, this is, it's not really anything statistical as much as it's process knowledge. So you think about what the distribution of those factors might be. We can use some tools to help identify these distributions and really see, what distribution makes sense. So like I said, for press, we're assuming that distribution is a normal distribution that has a mean of 20. What I'm going to do is, in this parameter optimization, I'm going to say, okay, go ahead and search around and search, what if the mean was as low as 18? Or what if the mean was as high as 22? See what that would look like in terms of how it affects my response for granule loss. Same thing with some of these other factors. There are some distributions, like viscosity, that because we've defined it using a truncated normal, that one's not available to use within parameter optimization. The mathematics just gets weird. But for other ones, you can see the search ranges are here. There's also this checkbox for noise, which I don't have any noise factors here. But in this case, if there's a factor that that you have in your process, you fit it into your model, but you can't control it, well, you still want to include it in the optimization, but we know it's going to sit at its set point. There's no manipulating that. Then I could just set that for noise. Okay. So it runs through the parameter optimization, and it basically runs through and tries to find the best settings for the factors. And you can see down here as part of the output where you've got the previous settings in terms of where we were at with the process. So we started in our first initial simulation was where the press was set at 20 with the standard deviation. And now after running through the search, it's setting that press down there closer to 18. So it's saying, okay, if you change these factors from these settings to these settings, this is what I predict will happen. And all you're doing here is running another simulation. So after running through the optimization and we find some new settings for you, we just go ahead and do it for you and say, well, we'll run it for you, see if you like it. And we run this simulation and say, okay, well, now I predict about 1%. So a little bit better capabilities, not great, but about 1% of these items will be out of spec. After parameter optimization, like I said, and you could run parameter optimization as many times as you'd like. The other thing you could think about is, from a practical standpoint, is, okay, it's easy to change set points. So I could change the press, and assuming I can change the press from 20 and set it down closer to 18 and get some better results. But sometimes parameter optimization only takes you so far. Changing those set points, does so much for you. The other thing to consider is what we call sensitivity analysis. And sensitivity analysis is, think about which of the inputs, if you could control the variation of those inputs, would reduce the variation of the Y. So if what's your troublemaker inputs that you could help look at, and that's what sensitivity analysis is going to do for you. So this graph might be the first time you see something like this, if you're not a user rep companion, because I think we do this in a pretty cool way. But basically what the graph shows is that at this center point, it's saying that this is assuming that the standard deviation of those values as they are right now. So whatever the set points are for those different factors, and it's saying that if I took, let's say this, one of these factors and said, if I reduce the variation by 5%, so all I'm doing for each one of these points is rerunning a simulation where I have assumptions for those input parameters, and now I'm assuming that the variation is just a little bit smaller for this factor. So for press, if I can reduce the variation by 20% or by 30%, what would be the expected result? What would be the variation in that response? So what you're looking for here is that you're looking for things that have big curves. Basically it's telling you that if I can reduce the variation by 50% of this input, then I could theoretically reduce the standard deviation down to about 30, or down for this response. So you look for things that it might have a big impact, and these are things that are important to control. Then you also look for things that are relatively flat. As the variation increases for some of these factors, something like sheet tension, in this case the green one, that would show you that as I increase the variation, it's really not going to make a difference on the variation. So that one maybe is more robust to things like that. So if you think robust parameter design is similar to kind of what we're talking about here. So let's say theoretically that I could reduce the variation in the press by 50%. And again, this is one of those things that this might be easy to do. This might be impossible to do. If you've got raw materials coming in and it's impossible to reduce the variation in them, then obviously that's not something that's an option for you as you're trying to solve the problem. Well, let's assume that I'm going to go through and run this where I'm going to say that, okay, if I could get the press down, if I could remove the variation by 50%, and also the other one, the moisture level, down by 50%. And again, just cutting it in half, what would that look like? So now all we're doing is going to rerun the simulation using these different assumptions, so slightly different assumptions. And here, making those assumptions, we rerun the simulation. So a third simulation here where I'm looking at the sensitivity and saying, okay, if you get the variation down, then I would expect that nothing would be out of spec, theoretically. Press capability is okay. Usually we want at least 1.33. But it's certainly better than where we started on that. So we think about that example. I had a single equation and a single response. So my single equation had 6 inputs and I had a response, and we developed that using DOE. But you can have an equation that was developed using process knowledge. You could have it developed using like your first principles, engineering process. It could be developed using regression, ANOVA, where I've got some model, I've got some inputs. But now think about if I extend this and say, well, okay, what if I have a process that's much more complicated, where I'm looking at a system that has, 4 different equations that help describe that system. One of the things in Companion that we've built in to kind of help you compartmentalize or organize simulations is the idea of groups. So you can actually create groups, and what those groups are, if you take a look at this, is where I've got a group that's referred to as assembly dimensions. This is a completely different example, but it's really just to illustrate the point, where I've got a group where I've got some equations and some inputs here. Then I have, a spring force, a section within spring force. Then I have a third section within operation. And then as I, think about all this stuff coming together, there's a way to look at all groups together. And again, this is that visual validation where I'm, here I've got, 5 inputs going into 2 outputs for my first group. And then at that second group, I had 2 more variables come into play, and that one of those outputs feeds into, my as now an input here for a different output. And like I said, as you think about these things kind of coming together, they could become really complex. And, we have some customers that are, have hundreds of input variables and lots of output variables. And it's much easier to organize the simulation when you utilize this grouping feature, not only from the engineering standpoint, but also organizing these pieces. it doesn't really matter because it's still going to run that simulation together. Like I said, there is no limitation on the number of inputs or outputs that you can run. So there was a question that, can we do Monte Carlo simulation just in Minitab or Companion? You can run Monte Carlo simulation in Minitab, but there's not a specific tool. So you would have to manually create the distributions, then make an equation in the calculator, you know, and put it in a column and run that. The Companion tool, which there's a free 30-day demo of it, actually does this in a very nice interface where you set up the equation, you pick the distributions, and very nice, you know, in terms of visualization and output. So I would encourage you to check that out. So really, like I said, the idea here with this engineering type example was really we used Minitab to generate the transfer function. And we did that using a designed experiment. And like I said, that could have been with regression, that could have been with other tools. But either way, the important part is that you have to make sure that if you're going to use simulation, you really are confident that you fit a good model. Once you fit that good model, then those inputs, really thinking about those inputs and really thinking about what is the distribution, what are those probability distributions of those inputs really look like? Because you want to get those right. Because if you guess wrong, then obviously your simulation results will be wrong. Then we just, you know, we just look at this and we simulate and we look to see what, you know, what's happening. So Companion really made it easy to like utilize that stuff and bring it all together. But like I said, you could use, if you were just doing Monte Carlo simulation without the parameter optimization sensitivity, you could certainly do that and put that in Minitab as well. So before we open, before we take some other questions, just want to reiterate some of the products that Minitab offers. So like I said, here we're talking about the simulation tool within Companion. But like I said, simulation in general, so whatever product you're using, you know, I'm sure you could use it, but there is a simulation tool within Companion that I encourage you to check out. Minitab 18, a lot of you are probably familiar with that, statistical data analysis. We also have a quality trainer, which is an e-learning tool that really helps you understand, you know, some basic statistic concepts that goes up through design of experiments. And our newest product, which is the Salford Predictive Modeler, which is really predictive analytics and decision trees, stuff like that. A lot of, like I said, services and support to really help you be successful. With support, there's other webinars, videos. I would definitely encourage you to check out the website in terms of the support. There's a lot of free content up there to really help you understand things. There's other videos regarding Monte Carlo, stuff like that.
Great.
Before we take questions, I'm just gonna, sorry, go ahead, Evan.
Oh, no problem. Yeah, I thank you for sharing that information on support as well. We'll, as a reminder, this is being recorded, and we'll send everybody slides after the presentation. And I think within those slides, we'll have some more information that you'll find on our support site about upcoming webinars that you can click right through there. Right here, we just want to talk about, you know, continuing the conversation with you if you're able to join us at our annual Minitab Insights Conference. This will be the third year that we are putting on Minitab Insights. This year, it's at the Scottsdale Resort in Arizona. You can get ready to share your knowledge, expand your statistical analysis and quality improvement skills, and network. It's September 12th through 14th. If you head on to that website, info.minitab.com/insights, you'll learn a lot more there. We actually have early bird pricing through June 30th. So, you know, you'll be seeing our program coming out there in a couple weeks where you can find out who's speaking, and you can save $100 if you register before June 30th. As well, we have expert advice in the Minitab lab. And new this year, we have a user-centered design studio. That's where we're going to have our top software designers there. They'll put you in the front seat to test drive our latest products, and you can give your feedback. So what features and capabilities would you like to see next in Minitab or Companion to help you run experiments, gain key insights, work more efficiently? We'll talk with you a little bit there about the future of Minitab software.
Thanks, Evan. So there were a few questions on the line, and I've been trying to answer some as I'm going, but let me circle back to a couple of them. One was a question about the model error, which is a great question. So in design of experiments or any regression, actually, you have your mean square error, and the question was why that's not wasn't incorporated in this. We don't have it formally put in, but you could actually add another term to add that error term in that would come into that. It would just be a random factor that would incorporate that MSE, and I believe it's good practice to do that, something we haven't just fully developed into the product yet. Let's see. The videos for quality or for the videos are on support pages, so you should be able to find all those. And could I does Companion read Excel data? Companion does not read Excel data directly, but I guess it would depend what you're doing. You can actually, Companion will export data. So one of the things that Companion would do would be if you want to take the data from Companion and move it out into Excel or into Minitab, there is a way to export the CSV file of the simulation data. So that's something that you could take, easy to do. And that's just under the file, under the export section. There's a couple other things. There was a question about the nature of the equations that you could put in Companion. We do have the ability to put logical operators in, so if, and kind of things to build more complex equations for that. I think I mentioned that there was no limit to the number of X's, the number of simulations in Companion, you go up to 1 million without any problem. And I think I also mentioned that there was the feature that either if you're using both Minitab and Companion, in Minitab you can do individual distribution identification to help try to figure out what the distribution is. In Companion, within the simulation tool itself, there's a specific, you're picking a distribution, you can actually use data to decide, and there you can feed in a CSV file, and it will go ahead and tell you if any of the distributions we have available are good fits. And we give you actually the top 3. So we'll tell you the best one, and then well, from a statistical standpoint, and then we give you the other 2 that look pretty good. And that's where you would use process knowledge to really decide which one of those makes more sense. But like I said, I can't stress the importance of don't just rely on statistics. You use, process knowledge and really make sure that things make sense from a practical standpoint. One of the questions was, is there a situation where you'd use regression or DOE to choose your transfer function? It really depends on the nature of how you analyze data in general, and is how you collect data is how you analyze data. So if you collected it in the nature of, of a designed experiment, then you'd want to, the analysis is actually very easy because of the nature of that data. But really, it doesn't really matter. How do you get to that transfer function really is just, what kind of data do you have, what's available to you, how confident how good that data is, and then being able to develop that, like I said, either using regression methods or DOE. Either way, Minitab statistical software has a lot of automated, methods that stepwise, to fit the model for you, where you can feed all the, different factors that you'd like, and then you can, it'll just run through and tell you what the best model is. So that's pretty convenient. Okay. I think we're almost at the end, and I hope I've answered questions. If there's other questions I haven't got to, we have your name, so I'll be able to follow up, individually. But definitely, like I said, if you're interested in, first of all, thank you for taking the time to come to the session. But there is a free 30-day demo of Companion, so if you want to try that out and see how that works. But certainly, there's a lot of other, information and stuff about Monte Carlo. But I hope you, like I said, hope you'll add it to your toolkit. Consider it next time, you're either fitting models, predicting projects. Anytime you have an equation and you have inputs and you think that there's uncertainty in those inputs, think about if this makes sense to incorporate.
Great. Great. Well, yeah, thank you so much, Jen. Yeah, and if we haven't answered your question, as Jen said, there's that free 30-day trial at companionbyminitab.com. We'll be looking through the questions after this and getting back to you. We'd also encourage you to contact our sales team or fill out a form on the site if you want to see more of a personalized one-on-one webinar sort of experience. We can do demos in that way too. And also I want to remind everybody, this is being recorded, so we'll send you the presentation in a few days, as well as the slides and some more links within those slides so you can see our upcoming webinars. We have one for Minitab coming up over the next couple months, a series of them called Minitab Need to Knows that we're excited to share with everybody. And also,
let me ask you one more question before we finish, Evan. Sorry.
Oh, sure.
So there's one more question that came in. The question was, does the tool have a way to save various scenarios? And the answer is yes. So as you create things in Companion, when you create different simulations, you're basically very similar to Minitab, if you're familiar with that, is that you're creating different levels of output. So I can run a simulation 50 times and I could have 50 different, I could either override my simulation I'm in, or I could make copies and I can, run that. So you can save as many different scenarios as you'd like. You don't have to overwrite anything, which is a little different than some of the Excel add-ins where you have to overwrite your results in order to run something else. All right, sorry, Evan.
Oh, no problem. I think that's great. And yeah, if you have more questions coming in, we'll get back to you guys on those. You can also contact us on the website. And finally, I just wanted to put in another reminder. When your GoToWebinar closes, when we end the session in a minute here, you should see a survey pop up. That's really going to help us continue to tailor our Minitab webinar program so we can just sort of know you as an audience and what kind of information you're looking to understand in the future. So please go ahead and take your time to answer that. We really appreciate you taking the time. And I want to say on behalf of myself, Jen, everybody at Minitab, I hope everybody has a great rest of their day. And thanks for joining our webinar today.
Thanks, everybody.
Thank you.